Hello, for this video lecture we're going to be talking about one-dimensional non-continuous motion. So non-continuous motion, oftentimes a single mathematical function cannot describe the entirety of the motion in the problem, either position, velocity, or acceleration. So when this happens, it's called non-continuous motion. We need kind of separate math functions for separate times. So an example of this might be, a car accelerates for a couple seconds, it holds a constant speed for the next couple seconds, and then it decelerates at a constant rate for the next couple seconds. So I've got these divided up into three sections, and each one of them is going to have its own separate mathematical functions. So I employ one set of equations, for position, velocity, and acceleration for section 1, another set of equations, position, velocity, and acceleration for section 2, a third set for the final few seconds of the whole time curve here. So using a graph or data and key points, we can also figure out the equations for each of these three sections. So here I've got velocity. I might figure out velocity equation for the first section, velocity equation for the next section, velocity equation for the third section. And that equation is only going to be valid for its respective time period. But we might be interested in more of these things. We might be interested in position during this time and acceleration during this time. So how would we figure that out when we don't have one constant equation for each of these? And analyzing this, we're going to start by drawing out the graph of position, velocity, and acceleration like we had on the slide back here. And these problems, I like to solve them in a very graphical way. So sometimes the velocity function, like the slide before, is going to be given to you. Other times you might need to figure it out based on key points that are given to you, velocity at certain times in that whole function. So either way, you want to figure out for this function here, what is the equation for velocity in that first section? What is the equation for velocity in that second section? What is the equation for velocity in that third equation? Once you have those three sets of equations, you're ready to go and figure out position, figure out acceleration based on that. So in that initial plot, make sure you draw out the equations, draw out the velocities at key points. The key points being those transition points where we are kind of moving from one section to the next section. Also, it's good to label each of those sections. I like to use Roman numerals to label those sections. So I've got section 1, section 2, section 3. So once we have a graph of one thing, so acceleration or velocity, we'll be taking the derivatives or integrals like we did before for continuous motion to find the other plots. So to find the equations for the first section, it's the same as you would for the continuous one-dimensional motion. So starting with velocity, if we take the derivative, we would get acceleration, and if we take the integral, we would get the position. And so we can start to draw out position functions and acceleration functions for these as well. So for the second section onward, it's going to be a little more complicated. So we can still take the derivative or integral of that function for the second section, but now those constants of integration aren't necessarily going to be obvious. So it's not going to be initial velocity, initial position. It's going to be it is going to be initial velocity, initial position, but it's at time equals 0, not that initial velocity and initial position at the transition point from one section to the next. So how do we solve for those constants of integration when they show up? And solving for those, we need to use the transition points. So for velocity and for position, we can't instantly change position, we can't instantly change velocity at any one point. So the velocity function is going to be continuous, and so is the position function. And this is because an instantaneous change in velocity or instantaneous change in position would require infinite acceleration and infinite force. So since we can't physically do that, we know that those lines need to be continuous in this whole thing. Additionally, the position is going to be kind of a smooth transition because an instant change in, or a continuous change in velocity means that I can't have a sudden change in slope for the position. So if we solve for the velocity or position at the end of one section, it's going to be the same as the beginning of the next section. And so this is kind of what it's going to look like with all of that. So what I might do for the, so say I have this velocity function here, I'm interested in position. So the line, if I take the integral of a line, I wind up with a parabola. And so I might try to find the position at the end of that first section because I know everything. So for this second section, the integral of a constant is going to be a line. In this case, a positive constant gives us a positive slope for the line down here. But the integral of a constant is going to be some line with a slope plus some constant of integration. And I need to solve for that constant of integration by looking at this transition time. So I know what the position is because the position at the end of this is the same as the position at the beginning of this section. So at that given time, you're going to plug in the known time, you're going to plug in the known position, and you're going to solve for the constant of integration. So once you know the constant of integration for this section here, you solve for the position at the end of this section, the position at the end of this section at the given time, you plug those two things in. That's going to be the position at the beginning of this last section. This last section is again a parabola because the derivative of a line, or sorry, the integral of a line is going to be a parabola. So we use those two knowns to solve for the constant of integration from this integral we take right here. We don't have that problem with acceleration, so when we take derivatives, we don't have a constant of integration. It's pretty easy to develop that. So this is a positive slope, a line with a positive slope, so positive constant. The derivative of a constant is 0. The derivative of a line with a negative slope would be just a negative constant there. So that's what we're going to be doing. You can look at some of the worked example videos to see more information on finding those constants of integration and developing these plots as well. So thank you for watching. I hope to see you again.